Good afternoon, everyone. I'm Jeremy Picot-Clemente, Photonics Technology Manager at EPIC. I'm really pleased to welcome you for this online technology meeting on VCSEL technology and application. So today we are going to talk together about VCSEL technology and how these technology are revolutionizing our lives and how this technology also is really involved in our daily life, from 3D sensing to augmented reality systems, including gas sensing and also optical communication. So we will address today, by giving the floor to research and industrial experts, the challenges of VCSEL technology. So I would like to remind you that it's a live event, so feel free to ask any question we have in the chat, Zoom chat, or by raising your hands through Zoom. So what is EPIC? EPIC is the largest industry association with more than 800 members working in the photonics field. So we try to act as a catalyzer for the photonics ecosystem by maintaining a strong network interaction between our members and organizing physical events and online events also, publishing markets and technology reports, organizing technical workshops, and with a lot of other activities you can find on our website. So here you can see the EPIC team made of 14 people passionate by photonics. So this team manages and supports all the ecosystem with their technology knowledges, market reports, proactive networking, as I told you, organizing physical and online events and easing the market access to our members. We are involved also in HR with a specific website, Jobs in Photonics, dedicated to the jobs for photonics industry, and also supporting the development and the investment in this industry. Just to have a quick view of the event we organized this year till January 2023. So we have a lot of events, and I would like also to highlight the event related to VCSEL technologies. We have also a physical event in September about CMOS compatible integrated photonics, Industrial Quantum Photonics Technology Summit in Glasgow. And we have also online technology meetings in September, October, November, and December related to VCSEL technology. So if you are interested, you can check our website and feel free to ask also if you need to be a speaker, or if you have the opportunity to be a speaker for this. Here are our sponsors for this event. So Modulight design and manufactures laser for personalized medicine, the only vertically integrated medical laser manufacturer in the world. Axetris. So Axetris is serving OEM customers with micro technology based infrared light sources, laser gas sensors, gas flow sensors, and controllers and micro-optical components used in industrial, telecom, environmental, medical, and automotive application. Instrument systems, which provide light measurement solution for development and production of high-end displays, LEDs, and VCSELs in consumer electronics, automotive, and lighting. We have also ficonTEC, which provides automated assembly or test of micro-optics and optoelectronics components, automated photonics packaging and testing system for high-end optoelectronic components and PICs. We have also SUS MicroOptics, which is a leading company for high-quality micro-optics, and the company comprises profound experience in optical design, microfabrication, and metrology. We have Focuz. Focuz provides manufacturing services with extensive experience in packaging and optoelectronics and precision electromechanical components, modules, and subsystems for OEMs. We have Avantes. Avantes is a company in the field of miniature spectroscopy and fiber optics application, and the company enables spectroscopy solution for VCSEL application. We have Vertilas. Vertilas is a leading provider of NIR laser, VCSEL diodes, and array for gas detection, sensing, and communication application in the wavelength range from 1.3 micrometers to 2.3 micrometers. And last but not least, fibeReality, which is an independent consulting and market intelligence company specializing in optical equipment and services in the telecommunication and data communications in space. So if you have any question, if you want to put in touch with this sponsor or speakers of today's OTM, feel free to send me an email, my email address here. And a quick view also on the value chain of today's OTM. So more than 180 people were registered for this OTM, from the components suppliers, semiconductor manufacturer, packaging, assembly, optics and micro-optics, to the end user and system integrators, including software and simulation, R&D laboratories, and VCSEL suppliers. So all these companies are in the room today, and this is one of the strengths of EPIC, be able to gather all these relevant companies to discuss the same topic. So yeah, again, feel free to take the opportunity to ask any question you will have during the meeting. And now let's see who are our panelists of this OTM. So I'm really pleased to co-moderate this event with Tracy Vanik, Head of Photonics Market Research at EPIC, and we'll have seven presentations today. Stefano Prandoni from Boundary Stands, Karthik Iyer from Instrument System, Ivan Zyulkov from Umicore, Christian Neumeyr from Vertilas, Nikolay Ledentsov for Six Systems, Ludovic Marigo from NIC Technology, and Rolin Roos from 26. So thanks again, and I will ask to Stefano Prandoni to share and to start the presentation.
Thank you very much, Jeremy. So let me share my screen,
yeah, you can start,
and kick off the session today. Okay, you should see my screen now. Let's go to presentation mode. And
perfect.
Yeah, ready to go. So let's start. Let me start from a very quick presentation of the company. So Bandwidth 10 was originally a spin-off from the group on the University of Berkeley, who was dedicated to the development of a specific patent for swept VCSEL tunable, and this is the product that it came out. So this is a patented technology. What we have, it's basically based on a MEMS that is a grating on top of the VCSEL. That it's called a high contrast grating. So it's a grating that can be moved basically down and can shorten the cavity. And by shortening the cavity, so you apply a bias on the grating. The grating moves down due to the electrostatic effect, and you shorten the cavity. By doing this, you can directly modulate electrically the wavelength, and you can tune the laser. This allows also for very quick and continuous tuning, which is a function that is called sweeping. So you sweep the laser through different wavelength with continuity, which is a difference compared to other lasers. Basically, so we have now demonstrated now for the 1060 nanometer, 73.2 nanometer tuning range. This is still prototype. As a product, we have today 50 nanometer tuning range at 1060. We have other wavelengths, so we have 1550, we have 1654. We have introduced now this month other two wavelengths. So we have 1310 nanometer and 1410 nanometer, and for every center wavelength, we have a specific tuning range. So this depends on the base material that we use. So for the 1060, we have a wider tuning range because this is based on gallium arsenide, and with gallium arsenide, it's easier to reach higher values for tuning range. For the 1550, 1654, 1310, and 1410 nanometer, we work with indium phosphide, and for this material, say the base tuning range we have is 10 nanometer. We can have premium. It's possible to select premium parts with 12 or 15 nanometer tuning range. Theoretically, our process can be used with wavelengths from 720 nanometer to 1700 nanometer. And as I say, the product that we have now in the portfolio are based on the active demand that we got from the market, which is basically for the wavelengths that I've mentioned. Now let me go to some typical applications that we see from the market as of main interest for different wavelengths that we have as product today. So here is a map of the wavelength, and divided by the wavelengths, you can see groups of applications. For the, let's say, 990 to 1080 is what is commonly known or mentioned as 1060 or 1050 center wavelength. For this application, the king of this application for the swept source is, of course, the OCT applications. Could be medical, for ophthalmology, which means retina imaging, biometry, and this kind of stuff. And there's also an industrial application for OCT, for the inspection of mechanical parts, semiconductors, different applications with different requirements. Then consumer electronics, there could be some related to OCT application, some application for augmented reality, biosensing, also glucose monitoring. Glucose monitoring is an application that you find also under other wavelengths. So for example, 1550 or 1310, depends on the technology and the approach that the company used. We have listed basically the OCT within the 1060 as king application because of the wavelength range that the tuning range that you have to have there. So it must be at least 30 nanometer. And for retina imaging, it should be beyond 70, 80 nanometers. So 100 nanometer is the common requirement. So we are working now for biometry and some, say, entry-level retina imaging. Then there's an OCT application also for the 1310, which is the front part of the eye, the diagnosis for the front part of the eye. And for the OCT for the eye diagnosis, the wavelength choice is determined by the absorption of a specific wavelength from the frontal part of the eye or the back or the retina. Then there's a minor request that we see now for wavelengths around 1400. So there's an atomic clock application for slightly lower than 1400. And for 1410, we received some requests for redundant wavelengths to add to the 1550 or other wavelengths for LiDAR. 1500 is, we have these wavelengths from the beginning because of the telecom application, and because also some of the sensing applications are central focus on this on the C band, on the telecommunications C band, because there is where the components, also passive components, can be found at the lowest price, because it's common technology, let's say so. And here, king of the applications is fiber break rating. It seems that there's a huge interest now in sensing application for spreaded sensing, sensing almost everywhere in infrastructure. There are some concepts to have sensors in every kind of big infrastructure. There are projects to have sensors everywhere in a city with buildings, bridges. Then there are other uses for wind turbine blades, railways. So basically, it's for monitoring strain and temperature variations or vibrations. And then all other applications like gas sensing, short range LiDAR, and 1654 instead is basically for methane sensing. This is another slide. So basically, it's the same picture, kind of tweaked. So I will share the slides for those who want to have a copy of it. I will not focus on this one. Then I have a set of slides for 3 or 4 applications. So fiber brake sensing I already mentioned. So this is becoming a mainstream application now for every big infrastructure or mechanical component. So wind blades need to be monitored for deformation, stress, mechanical stress, and also to get the maximum possible efficiency from the turbines. Railways, okay, speaks for itself, and other application also interesting. TDLAS is gas sensing. I think it's also common understanding how it works. You have some specific gases with absorption lines. We work for methane with the line at around 1654 nanometer. There are also other lines available. We work with that because our substrate can target that wavelength. And then at the moment, for us, the most interesting probably, together with FDG sensing, is swept source OCT. Here you see some scans of skin. You can create with swept source techniques a 3D image of almost any surface absorbing this specific wavelength, and for the eye is 1060. We have developed now a prototype that we have shown at a couple of exhibitions lately, and it's an OCT so-called engine. It's an amplified source, and with this one we could take this image of a retina of an eye, and this is very interesting. It was great success for us. I think I've already passed my limit of for the time, so I have other slides. It's basically describing other results with our OCT box, and then it's just this is on the left myself, and on the right the application engineer based in Berlin. We are in Germany, and this is the team supporting a European project. So sorry for the 4 minutes longer.
No, that's okay, Stefano. Thank you very much for your presentation. Really, very impressive to see how many applications we can address with this kind of technology. So, any question for Stefano on WIF10, please? Raise your hand through Zoom. Okay. We have one question, please. I can't see. Eric, if you want to ask.
Yes, Eric Mazalera from ST Micro. In one of your slides, you mentioned fast tunable swept source and multiple wavelengths sources. It's not clear to me the second category. I mean, you are able to provide devices with a wide range of illumination, or just centered on one particular wavelength, plus minus 70, 80 nanometer?
Hi, Eric. Thank you for the question. So basically, it's the second option that you say. So we can provide sources for gallium arsenide. The tuning range could be wider. So let's say 50 nanometer and beyond could be possible. And for other wavelengths based on indium phosphide, the tuning range, let's say it's on average 10 nanometers. Then we can offer different sets of center wavelengths. So it's different sets. So if you want to have a laser at 1520, we can give you a laser at 1520 plus minus 5 nanometer, for example. If you want to have a laser at 1600, we can give you a laser at 1600 plus minus 5 nanometer. If you want a laser at 900 nanometer, so we have a standard centered at 1050 plus minus 25. You could have as a custom product a 900 center wavelength plus minus 25.
Yeah,
this is more or less, yeah, easy explanation.
And maybe a more, let's say, problematic question for you. What about volume production? Do you have some order of magnitude of the cost, or do you have some projection for high volume?
So we have our own fab in Taiwan. So the volume and the capacity is not a problem. So for the 1550, we have now a capacity of millions of chips.
Okay.
And this is 1550 is a general available product. The 1060 is in beta stage, so the yield is still relatively constrained, or the capacity is relatively constrained. After the GA, also the 1060 will become available with the same yield and same capacity as the 1550, because the fab is the same. And the fab was dimensioned at the beginning for telecom applications. So for sensing application, for example, we don't expect to have actually any constraint, because the volumes usually, so if you talk with the telecom players, I mean, standard volumes are hundreds of thousands or millions of parts. For sensing applications, what we hear is, so an application with high volumes is sometimes 1,000 or 10,000 pieces, which doesn't affect at all our capacity.
Okay, thanks.
Okay, thank you, Rick, for your question. And yes, Wilfried, you had a question.
Yeah, I have a question. Yeah, thank you. I have a question concerning the OCT versus LiDAR. You mentioned LiDAR. So in terms of requirements, power, stability, is that a very different LiDAR to OCT, or is that the same product for you?
So yeah, it's thank you for the question, Wilfried. Actually, yeah, it's tricky to answer, because for us, OCT and LiDAR are two very different applications. The product is the same. I have to say, so we have with our standard laser source, it's a VCSEL with pretty low power. So we're talking about 1 milliwatt for the 1550 and 0.2, 0.3 milliwatt for the 1060. So for the 1060, which is used for ophthalmological OCT mainly, you need to amplify it. So you need an SOA, and the OCT application for ophthalmological use, for example, requires 15, 20 milliwatts as kind of standard. This is more or less the same. So for industrial application, depends, could be slightly lower. So I have projects requiring 10, 15 milliwatts for industrial OCT. Still requires an SOA. For the LiDAR, yeah, it's complicated, because actually with our lasers, we can address only short-range LiDAR application, means the order of 3 to 5, maybe 7 meters without amplification. And with amplification, so one of the application that we could target with our sources could be, for example, LiDAR mounted on robots in fab environment, where you have the presence of human beings and machineries moving together, and you have to work with, let's say, it's the advantage of the LiDAR based on a swept source. So it's a different approach. It's an FMCW LiDAR approach. As the advantage, what we understand that you can measure different parameters at the same time. You can measure the distance and the acceleration, which I understand it's not easily possible with other techniques. What we don't have, and usually doesn't make sense to have, is the power. I mean, we are not addressing automotive applications with our lasers, because if you add an amplification to the laser, the cost will be already too high for an automotive application. So it could make sense for pedestrian areas if you want to monitor very close objects, but must go together with more powerful lasers.
Okay, thank you. But you probably can have a very precise distance measurement because of your frequency ranging.
This is the advantage. The advantage is not only the frequency. Yeah, it's the FMCW approach. I mean, the wavelengths. I mean, it gives you the advantage with the modulation to have more precise measurement.
Okay. Thank you, Stefano. Thanks, Wilfried. We have another question in the chat from Carlos Viana. A short question and a short answer, please, Stefano, if you can. Carlos, if you want to ask your question by yourself.
Sure. Thank you, Stefano, for the nice presentation. I was wondering, since you are using a MEMS on the VCSEL, if in terms of packaging, if is any challenge, any constraints in terms of fiber coupling or fiber attachment, or sensible, how much sensible it is then?
So if you want to attach something directly on the chip, today with the design today, it's impossible, because you would the output mirror is also the grating, is also the MEMS. We are working on a new design, which is a flip chip design, and the grating would be in that design the back mirror. And in that design, you could use the output mirror also to attach a lens or fiber directly on the chip. And this should be available, let's say, in 1 year from now.
Okay, thank you.
Thanks, Carlos, for your question. Tracy, a short question.
Okay, I'll make it quick. Just Stefano, thank you so much for this presentation. You gave a very comprehensive presentation on some of the new applications for VCSELs and the technology that you're applying. One of the things I had a question about that was on TDLS. The materials that you're using for TDLS, are you using any MCT, or are you instead choosing a specific material? So are you doing tunable MCT or a specific material for each gas that you want to sense?
No, so actually the TDLS that we have was originated, so that this wavelength was originated by a proactive request we had from a specific customer who wanted to have that wavelength. So we are working. So today we have only that one specific for methane gas. The material that we use is indium phosphide for the chip, as for the 1550, and I don't know if this answers your question.
It does. Thank you so much.
Thanks, Tracy, for our questions. And thanks again, Stefano, for your presentation. A lot of interest. Thanks a lot.
Thank you very much, Jeremy.
And now welcome Karthik Sureshaiyer from Instrument System. Karthik, if you want to share your presentation.
Hi, everyone.
Yes.
Hope everybody can see me, hear me, and see my slide.
That's perfect.
So good afternoon. Thanks, Jeremy, and the entire EPIC team for inviting us to speak on this OTM on VCSELs. So my name is Karthik Iyer. I'm the product manager for VCSEL and infrared portfolio testing systems at Instrument Systems. And today I'll be giving you a bit of an applicational view with respect to our entire VCSEL testing portfolio, namely the polarization, characterization, and the laser eye safety assessment of VCSELs. So a quick introduction on who we are. Instrument Systems provides a large range of measurement solutions for various industrial applications like display manufacturing, infrared and VCSEL, also in the automotive sector as well. We're based out of Munich. We have a site in Berlin as well. And we also have a global network of distributors and calibration labs all across the globe. Now, diving straight into the focus topics of today, starting with the polarization characterization of VCSELs using our VCSEL testing camera, the VTC 4000. So the VTC 4000 is a camera that can be used for the near field characterization of VCSEL, and it comprises of a CMOS sensor and microscopic optics. Now, in general, CMOS sensor and simple lenses, they are designed in such a way that their output is actually polarization independent. But in the real world, actually, when you combine these into a measurement system, you do see that there is a polarization dependency, especially on the pixel count. Here, I would like to show you a quick example on the left, if you can see. So here, it's a comparison of the total power measurement with different polarizations, with each of these dots representing one measurement. So what we did was we had a linear light source and we rotated it in 45 degree steps. And as you can clearly see, the sum of the pixel counts, there is a variation in it by at least, 10%. So how do we correct this polarization correction? Because these are important correction that needs to be accounted for, that needs to be done, especially for measuring absolute power measurements for a VCSEL, which in turn then are relevant or very much relevant for laser eye safety assessments. So what happens is that our polarization correction takes place in the form of an inline analysis of the emitted light and corrects the polarization dependency of the entire optical system. And this is done through a unique calibration concept that we have developed with the VTC 4000. And bear in mind, this is this entire procedure is then also traceable because we calibrated absolute, and it's also traceable to national standards. So once we do such a polarization correction, as you can see here on the right side, it's the same measurement that we did on the left side, except that now the polarization correction has been applied, and these effects, the polarization effects of VCSELs that are for typical VCSELs are pretty much inherent, they are corrected for. So here you can see that the intensity does not show any polarization effects anymore. And you can calculate these values back to watt, so the power, independent of the polarization of the incoming light. So from the polarization light or the light coming from the VCSELs. So as I mentioned, these are really important corrections that need to be done or must be done to ensure ensure really good absolute power measurements for laser eye safety calculations, for example. So here are some examples of with the VTC 4000. So we took a bunch of samples that are polarizing unstable or polarization unstable, and also certain samples that were polarization stable. So some kind of grading technique that have been that these VCSELs have undergone. And as you can see, so the unstable, it's pretty clear that these polarization they are inherently unstable. So within also each single emitter of a VCSEL, you can see that the polarization dependency or the behavior is pretty random. So the neat thing of this entire calibration concept is not only does it correct for the polarization effects, you can also measure the degree and angle of these VCSELs or of each single emitter within a VCSEL array, for example, as you can see here. And here below you can see that a polarization stable, how stable these polarization VCSELs are. So what I want to tell you is that this is a very comprehensive, fast, accurate method. It's a one-shot method to analyze such polarization controlling techniques, or to also observe the polarization behavior or the randomness of the polarization behavior within each VCSEL array or at the single emitter level. Here are some more examples. So we took the polarization stable VCSELs and we measured it at different currents, because we also know that polarization states can change very much depending on temperature or even bias current. So we changed the currents as well, and we can see how good the polarization stability of these VCSELs are. And this was all one-shot measurement, so extremely fast and of course extremely accurate. Now going into the second part of the application, that is the laser eye safety assessment. So we all know laser eye safety. So it's basically to determine the fraction of light that is absorbed by the eye or the imaging on our retina. And all of these VCSELs, they're laser sources, and most of the laser sources that are being used in the consumer electronics, for example, they need to be laser eye class defined and assessed, and of course they need to also have laser class 1. So here's a quick overview of the entire flowchart of the laser class assessment. I would not go into detail here. For detail, you can of course visit our YouTube channel, and we have a very detailed explanation of the entire assessment. I will be sharing the presentation as well, and here you will have the link. So there in detail, it's been explained how a laser class assessment actually is done. And taking from that, if I want to shrink the entire process of the laser class assessment into the most essential and bring it down to the most essential parameters that you need to have the value for to assess your laser class or determine your laser class, that would be these 7. So wavelength, your array size of the DUT, average power, beam profile, your divergence angle, the maximum intensity spot within an area, and of course the temporal characteristics like the repetition frequency and the pulse train, so on. So we have our entire portfolio, as you can see here. So we have the far field, the near field camera, and a high resolution spectrometer, and all together combined, we are able to provide all of these most essential parameter values. So just to give an example, so we measured an iPhone 12, a commercial iPhone 12 Pro, and we all know that iPhone Pro 12, it has VCSELs on the front and the back. The back has more as a LiDAR scanner, short-range LiDAR scanner, and the front also has like proximity sensors and stuff like that. And here we have, like in the front, we observed 3 sources. And just to give you an idea about how we measured or how we assess the laser class of these sources on the iPhone 12. So I will show you an example of the front sources. I won't show both of them. So basically, we took a look at these sources in the front of the iPhone 12, and we did a near field analysis. We did a far field analysis. We did the temporal analysis with a fast photodiode here, as you can see the DC, the pulse width, and the pulse train. And of course, we had the high resolution spectrometer as well to determine the spectral characteristics. There are possibilities to combine, for example, the near field camera with a spectrometer so that you get the wavelength and the pitch and the emitter size, the beam quality, the divergence angle all into one system, for example. So we have a very bright portfolio. And we kind of measured each of these parameters that I mentioned before, which each of these with a combination of these systems. And this is one thing that I want to mention very specially. So we have a feature called as the automatic hotspot detection. So as we know, so the radiant intensity of the VCSEL, so it's not homogeneously distributed. So the laser norm states that we need to find out the power that needs to be that is relevant for the laser eye safety determination. It needs to be through a 7mm aperture at a distance of 100 millimeters. I wouldn't go into details for that. And this is exactly what our software does. So it has a function where you can get the automatic detection of the maximum intensity within this area, in a way that it is actually looking through a 7mm aperture at 100mm distance. So this is an important parameter, or one of the most important parameters, as you guys know, for the laser class assessment. And in the end, what do? We collect all of these information, all of the values for these parameters that we get, and then we have a laser eye safety tool or a software where these values are inputted, and then it just determines. We have the entire algorithm and the entire calculations behind this tool, and it just kind of outputs you what kind of laser class your light source has. I mean, here is just an example, but it was it was not surprising that the VCSEL from the iPhone 12 Pro was classified as a class 1 laser. And at the end, what are the take-home messages? So as I mentioned, VCSELs are lasers, so they must comply with the laser eye safety standard. And compared to the normal lasers, so the normal lasers, they can be irregular, they can be multimode, they're divergent, they're often extended sources and not, they're also often pulsed, so they can be used in continuous wave and pulsed form as well. And you have two different kind of ways how to measure laser class assessment or laser class evaluation for the modes of its operation. One thing that you can do is that you can assume a worst case assumption. You can do a worst case assumption saying that, okay, my laser, my source in the consumer electronics, for example, it does not have a laser class 1, which then kind of shrinks your entire effort. You don't have to do the entire the huge peripheral of devices, so you don't have to use it. So you comprise it and into its basic parameters, but that may, on the other hand, lead to restricted values for the accessible emission limits. So it's kind of a balanced game. So you need to know what are you looking for. So you can do the entire peripheral and then you're 100% sure. And on the other hand, if you want to reduce your effort, you can go with the worst case assumption and then say that, okay, it's not meeting that criteria. And biggest and one of the most important thing is that for these measurement values to be valid, you have to choose calibrated and traceable measurement equipment that satisfies the norm. And that's exactly what we have. So all our devices, they are absolutely including the 2D camera, the absolute power that you get from the 2D camera. I'm not talking about the spectrometer. I'm not talking about the photodiode. I'm actually talking about just the 2D camera. That is also absolutely calibrated and also traceable to national institutes. Yeah, thank you very much for your attention, and yeah, hopefully it was informative on what we do. It's a view from the other side of the VCSEL, so we view the VCSELs, as they say. And yeah, thank you, and I'm open for any questions you guys may have.
Thanks a lot, Karthik. It was really interesting to see your presentation. And just a quick question. Your customers, they are manufacturers, VCSEL manufacturers, but they are also end users and system integrators. Yeah.
Yeah, so we actually have, we supply our devices for the entire value chain. So starting from wafer level testing, so where we have the VCSEL manufacturers come into play, and up until the end users and also system integrators. Yeah.
Okay, great. Very interesting. So do we have any question for Karthik? Yes, Christian Neumeyr from Vertilas, please.
Christian, you're muted, I think.
Yeah, you are muted.
Hi. Yeah, thanks for showing your great products. You showed these measurements about polarization and all the other near field, far field parameters. Can you do this for like single emitters, or can you do this with your tools also for 2D arrays?
For both, so we can do it at a single emitter level as well, and also for 2D arrays. Yeah.
Is there in like a maximum power limit or something your detector can go for? Or?
Yeah, so we have the wide range. So so if you take the photodiode, for example, where we have the integrating sphere and the photodiode, so we can go up till using an attenuator. For example, if we have an attenuator on the photodiode, we can go up till say 15 watt, 20 watt as well. So we on the 2D array on the single emitter level, of course, we are a bit more on the lower side, of course, but for consumer electronics, of course, it doesn't go into the higher watt range. So you have your classic 2 watt, 3 watt VCSELs that you have, which definitely we can measure.
And what wavelength ranges can you cover?
So right now, the near field camera, we offer a wavelength range of actually 910 to 980. So we concentrate on the classical 940 nanometers for the consumer electronics. But on the spectrometer and on the spectrometer, we go from right up till the shortwave infrared up to 1.5 mu, for example. And we are also on the far field. We are coming up with a product to cover the 1380, for example, under display applications. We are coming up with a product for getting the shortwave infrared light sources as well.
Right. Okay, thank you.
Thanks for the question.
Thank you. Yeah, thanks, Christian. We have a question from Ludovic Marigo, New Technology. Ludovic, do you want to ask your question by yourself?
Yes, sure. So the measurement that you showed the iPhone was at the field level, or did you remove optics which was on top?
Oh, yeah, we can't hear you really well.
Oh, okay, I thought it was just by me. All right.
Okay, I'm trying to get
No, it's
microphone. Hope it's good there. Oh, no. Sorry for that. Should be better now.
Okay, that's better. Yeah.
Yeah, I wanted to know the measurement that you show about the iPhone. Was it really at the module level, meaning with the phone, or did you remove the optics?
So, without divulging too many details, yes, it was both. So we could do both. So we could do it with the source on the phone as well, and also at the module. Yeah.
Okay. And do you offer the service, for example, of characterizing a module level? Or do you really focus on the instrument itself?
So we focus on our instrument, but we were more than happy to, like, we have a bunch of customers coming in with when they want to characterize their samples, and we do have offered in the past where we say that, okay, you can send us our samples, and then we characterize these samples against a code. But it is something that is not our main focus area, but it is something that we have, of course, done in the past.
Okay, thank you. Interesting.
Ludovic for a question. And Nikolay Ledentsov, please.
Hello, thank you very much for the presentation. I have a short question. Maybe I missed that. What is the maximum resolution that you have on the polarization resolved near field measurements?
So we can go up till 20 mu. So on the VCSEL itself. So it's very it's well resoluted. So we have a 12 megapixel camera on it, on a CMOS sensor on it, and yeah, we can go really low on the single emitter level.
So, but 20 micrometer is actually not much at all, because if you, for the sensing VCSELs, of course the apertures are large and there are many of them. But if we're speaking about single emitter, then for example, our company works on datacom VCSELs, and there we have, for example, a single emitter, and the aperture is maybe like 6-8 micrometer total. So to see the individual polarization modes inside this aperture, we would need a 1 micrometer resolution. Is it possible in the future, maybe?
Yes, we have. We have, of course, looked into it, and right now we have a project that is not yet completely up and coming, but we are looking into it to even resolute even more. But right now, that is not where. I mean, our focus has been up until now not so much onto the datacom VCSELs, but more into 3DS that sector.
Okay, so if you can contact me after the meeting, and we have a setup where we can resolute it, but without polarization measurements. So maybe just installing your camera in the setup would allow us to do it. So maybe we can cooperate on that. That would be great. Thank you.
Yeah, that would be great. Yeah, absolutely. Definitely. I will follow it up. Yeah.
Thank you.
Yes.
Thank you.
We'll be pleased to put you in contact, and Nikolay and Karthik. So yeah, thanks again, Karthik, for your presentation. Really
my pleasure.
And now we move on with Ivan Zyulkov from Umicore. Ivan, are you here?
Yes. Hello, everyone. I will not use the camera. I'm a little bit under weather today. Also, if my voice will do something weird, you know the reason. But I will start sharing. Can you see my screen?
Yes, let's try the presentation mode.
Absolutely, yeah.
Yes, that's okay. You can start. Thanks.
All right. So, hello everyone. Today we'll talk about germanium-based VCSEL technology and germanium substrates. So, but before I dive into the technical part, I want to introduce our company. I work for Umicore. At Umicore, we have several business units that can be grouped into three, let's say, main pillars. So one pillar deals with catalysis, and their typical product that we have is palladium-based catalyst that can be used in for diesel engines to trap NO2 gas and limit the toxic emissions. So the second pillar is energy and surface technologies, we call it, and there, for example, we are working on cathode materials, solid-state batteries, but also here we have a business unit called electro-optic materials, which I represent here today, and I will talk a little bit more about it. And then we have a third pillar, which deals with recycling. So that activity started with recycling of precious metals, like gold and platinum and palladium as well for catalysis. But now we can recycle more than 22 different metals. And in principle, in our activities, we try to use as much as possible recycled materials, and that relates to germanium as well. So now a little bit more about electro-optic materials. So there, in our business unit, we have 4 products and services. So 2 of them are related to germanium. So we have germanium products such as germanium wafers of various diameters. Also, we are a volume manufacturer of GCL4. This is high purity chemical required by photonics industry in order to dope the core of the optical fiber. And also we do germanium crystals. As germanium services, we do recycling. So actually we recycle hundreds of tons of waste in order to extract germanium out of there. A typical example is actually the byproducts of optical fiber industry, but also for solar cell customers, when you make the solar cell, any powder, any dust, any slurry, so liquid and solid waste can be recycled and germanium can be extracted. And also we have products related to infrared optics, so we do lenses and optical coatings. But so my today's talk is devoted to germanium products and wafers specifically. So now to put us a little bit into historical perspective, so probably we all know that VCSEL application started in 90s, and that back then it was for telecom on small substrates, let's say 2 to 3 inch. And there, so it was relatively straightforward. So it's homoepitaxy, you grow gallium arsenide on gallium arsenide wafer. And typical issues of gallium arsenide wafers, such as dislocations or the bow that we will talk about later on, back then they were not as pronounced. So then there was a migration to 4 inch, but actually things started moving fast when Apple introduced VCSELs into the Face ID on iPhone X. And there the transition to 6 inch started, and also iPhone 12 Pro when LiDAR was introduced on the backside. So there the transition to 6 inch happened, and there we start to see also more problems. So this is a very nice slide from Cardiff University, where they observed the bow of the 150 millimeter wafers, and where they compare germanium wafer and gallium arsenide wafer. So what is happening is you have your DBR stack, and DBR stack consists not only of gallium arsenide, of course, but also of aluminum arsenide, right? And there you have little lattice mismatch, and because of that, the stress builds up, and you start to bow your wafer. So these problems, they of course solved in the current production, which adds certain cost. So, but now if we look further, what we see already now is that IQE announced world first commercially available 8-inch VCSEL wafers, and these are germanium wafers and gallium arsenide wafers. So actually you can choose. At the same time, we also see lots of investments into automotive LiDAR systems. So for example, this is the article of Sabir Rangivala. He writes about LiDAR systems, very nice overviews actually, and here he reports recent progress on automotive LiDAR systems, and mind-boggling amount of investment that goes into that industry. And also, if we're talking about germanium, then we can envision also with 12-inch wafers, which would allow even for lower cost manufacturing. So this is, let's say, a vision. So now, if we go into more details and do a comparison of the substrates, so germanium substrate for VCSELs and gallium arsenide substrate for VCSELs. So here, first page is a sort of a summary of physical properties, starting with the lattice match. So the lattice constant of gallium arsenide and germanium is very close, but there is a small difference. So as I mentioned, gallium arsenide lattice constant is a little bit different from aluminum arsenide lattice constant, and germanium sits right in between. So because of that, when you start to grow your heterostructure, gallium arsenide, aluminum arsenide, if you do it on germanium, you're almost stress neutral. And in combination with a stronger, with a high strength of germanium as a material, you get much less bulk. So actually, it's about an order of magnitude less. And this is a comparison performed by IQE on 6-inch germanium wafer and 6-inch gallium arsenide wafer with the same VCSEL stack. So then in terms of dislocations, germanium is an elementary semiconductor. And because of that, the wafer making process is very similar to silicon. And in fact, you can make it dislocation free. So every product, every germanium wafer that we sell is dislocation free. So it's true EPD, true zero EPD. You have none of them. With gallium arsenide, there are also ways how to significantly decrease number of dislocations, if not to get rid of them completely. But that, of course, first of all, increases price. And second of all, you still have some dislocations left there. So now, in terms of sustainability, I mentioned that germanium is recyclable, and in fact, the recycling process is very efficient. So you can recuperate most of the cost back, and also it's not toxic. I think now, even in weird enough, in Asia, I think they even use some kind of food supplements with germanium. Not sure that works, but that shows that it is really not a health concern. So in terms of gallium arsenide, arsenic is toxic, and arsenic gets landfilled. And I mean, first of all, it's not good for the nature, and second of all, it requires permits and utilization costs. So this is again an extra cost of your manufacturing. So now looking at other parameters, so of course there is wafer cost, and cost of VCSEL quality wafer, germanium and gallium arsenide is on par. However, the cost structure is different. So in case of gallium arsenide, a more significant portion of the cost goes from making the wafer. So the transformation cost is high. In case of germanium, a significant portion of the cost is material price, because germanium is expensive material. But that's a portion that you can recuperate. So cost is on par, but if you consider recycling, then you can go less in cost using germanium wafers. So now, in terms of wafer size, I mentioned that germanium wafers are available up to 12-inch. So with Umicore, we can manufacture 12-inch wafers. We don't do it at scale because right now there is no demand, but it is possible. And one of the reasons, again, is just because it is very similar to silicon wafer manufacturing. With gallium arsenide, that there is limited offer on the market for 8-inch gallium arsenide, not talking about 12-inch wafers at all. Now, there is another factor which I think is rather interesting, related to CMOS compatibility. So, now there are two worlds. One is compound semiconductor manufacturing and compound semiconductor foundries, and then there are CMOS foundries as well. And these two worlds, they are not really talking to each other. And one of the reasons is, of course, that wafer diameter is very different. So if CMOS foundries, they mainly operate with 8-inch and 12-inch wafers. Compound semiconductor world operates 4-inch and 6-inch. But also because of the contamination requirements. So at CMOS foundry, they would not welcome you with arsenic-containing material to the fab. So, if you think about it, germanium is CMOS compatible material. So it's used in a gate stack. It's level 2, so it's, in terms of contamination requirements, it's absolutely fine with CMOS foundries. And then in terms of wafer diameter, you can, as I said, you can go for 8-inch and 12-inch. So which makes it CMOS compatible. So there you can envision certain things like you can process your wafer in CMOS foundry, or you can do integration with silicon drivers at the wafer level. So there are interesting things that can arise from there. And then there are other factors, of course, to be fair enough, gallium arsenide is a standard industry solution these days. In terms of germanium, probably something that was not mentioned and doesn't fall into any of those categories is also the fact that so germanium has high electron and hole mobility, which allows for different VCSEL designs. So we did not discuss VCSEL design, but because both electron and hole mobility is high, you can do things like you can, for example, put your N-type DBR down, or you can put your P-type DBR down if it gives you any advantage, which you cannot do with gallium arsenide. You can only put your N-type DBR down. So this is the end of the summary. Thank you for your attention. And here I put my contact details. So in case you want to reach out and discuss via email or a Teams call. Thank you.
Thank you very much, Ivan, for your presentation from the material side. It's really great. And we have already one question from, oh, okay, I saw a hand raised. Yes, Eric Mazalea from STM Microelectronics. Yeah, you are muted, Eric.
Thanks for the presentation, Ivan. I have two questions. One is related to the title of your presentation. I think it was a germanium-based VCSEL, but you have shown the advantages of, let's say, using germanium, but you haven't shown any performance of the VCSEL. Okay, can you comment?
Yes. So in fact, IQE started performing these tests, I think last year. They reported first VCSEL performance data, if I'm not wrong, on Photonics West last year. So back then they were doing it on 6-inch. And this year on CS Mantec, they also gave a presentation about 8-inch VCSEL performance on germanium versus gallium arsenide. So, we are wafer manufacturer, so we didn't go as far, but we follow closely what IQE is doing. And there we saw that actually performance, at least on 6-inch, it was very similar. 8-inch, they also reached similar performance, and they are continually working on improvement of this technology. So I think the point there being is that, on 8-inch, you have even more bow than on 6-inch. So you have more problems in your manufacturing doing it on gallium arsenide. Plus, I think that one of the advantages that they're considering where germanium can win actually in VCSEL performance is when you do longer wavelength. So there you have to have even thicker DBR stacks. And again, you have even more problems of making your wafer straight. You put even more stress compensation layers in the back. So,
So my second question is obvious now. So why is the standard now using gallium arsenide wafers instead of germanium? Because it seems germanium is let's say full of promises.
Right. So I think the answer is
cost or what?
So no, it's not the cost. It's just that. So there are fabs, compound semiconductor fabs that were designed and they are operating on gallium arsenide wafers, and there are still enough capacity in the production. So now, we were also kind of naive maybe at the beginning, thinking that they can immediately switch to germanium wafers, seeing all those advantages. But what we start to understand now is that there is a certain hurdle of qualification. So if you change your material, you need to do additional qualification, and right now they are not doing it, for at least for the standard products. At the same time, so we're talking across supply chain, and we see some signals that, in fact, for new products and new applications, there is an interest in doing it on germanium instead of gallium arsenide. So maybe, more simply put, if you have your running production, you don't really want to touch it. You don't want to change much. But if you're starting up something new product, new production line, there it definitely makes sense.
But do you have any idea of the type of new applications we have in mind?
Well, there are several applications. One of them indeed is long wavelength products. Also, of course, any automotive applications that would require high volume and larger chips would also make sense, because then, if you're thinking about cost roadmap, so let's say 5 years out, then that's a way to decrease the cost. You just go to larger wafer diameter.
Okay.
So that would be another one, yeah.
Thank you.
Okay.
Thanks, Eric, for a question. Thanks a lot. And we have another question from IQE. Iwan Davis, please.
Oh yeah, thanks. I just wanted to take the opportunity to thank Ivan for his presentation and for mentioning IQE on several occasions. If anyone is interested, I do have a couple of slides ready with some epitaxy performance, at least some characterization on growing on gallium arsenide against germanium. But I think we should dwell on the positive aspects of growing on germanium, which is, as Ivan has mentioned, the fact that you can grow on potentially larger diameter wafers, and you can increase that compatibility with CMOS processes in integration, and without any detriment to device performance or any materials characterization. So, plus then you have the added benefits of the toxicity aspects and so on. So I think we've looked at more the positives, particularly the wafer bow, as Ivan mentioned, and the quality, the substrate, the morphology is much better. So we've, as he has pointed out, we've published quite a few papers this year on initially the 150 millimeters, and then more latterly a few weeks ago on 200 millimeter wafers, albeit both gallium arsenide and germanium. But we see that there is at least an equivalence in performance on germanium to gallium arsenide, plus of course those additional benefits, potential benefits.
But yeah, maybe a question for Ivan.
Yeah, just another question from Mark Kotvitz. He was first. Mark, if you want to ask your question, please.
Sure thing. I appreciate it. I think we have to keep things in perspective. It was a minor miracle that WinSemi was able to pull off 6 inches on time for Apple at the 11th hour. And Apple still needed to go to finish off for 4-inch wafers because there were problems at the beginning. I don't think there's really as much demand for going to higher sizes or anything like that. The example of automobiles and LiDAR has spoofing and cost problems. So, that alone needs to be taken into consideration. But I just do not see, I think this is a Hail Mary. I don't see any demand for going beyond 6 inches right now.
Yeah, there are definitely different opinions. We hear in the different signals, or let's say mixed signals from the supply chain from time to time. Related to automotive, it's the same story. But what we see is, as a part of a roadmap, at least, for the cost decrease of the VCSEL part of the LiDAR module. That's maybe what I can comment on that.
Yeah, thanks, Mark, for your comments. And Eric, you have a last question?
Yes, please. This is maybe a question for IQE representative. So, from what I understood from your let's say comment, IQE, is that maybe even for traditional application, I mean, not only for longer wavelengths, germanium could present some advantages and could be produced soon. Am I correct? Or?
Yes, yeah, absolutely, that is correct. I mean, I think it's reasonable to say that we are still in the early stages of development, but the epi wafers, as we have announced a few weeks ago, epi wafers are commercially available if required, at 200 millimeters as well as at 150 millimeters. So it is, and as I said, with the what is very clearly an improved materials characteristic, and growing out to the longer wavelengths, where Ivan has correctly stated, the structures get a lot thicker as you go to longer wavelengths. So that again plays more into the germanium, the germanium process, with its improved lattice match to the thicker stack, and less stress, less wafer bow, and so on. So we are seeing that the traditional applications would still blend themselves just as well to the larger diameter germanium wafers, as well as those newer applications, I think, such as long wavelength LiDAR and so on. And I can only echo some of the comments coming from our customers, who I cannot name for obvious reasons, but I do share that there is potentially some skepticism amongst the group. But I think there is a big potential for this.
Thank you. I have over question, but
yeah. We don't have a lot of time now, but I would like just to let Karthik to ask your question.
Yeah, it's hopefully maybe I missed that. What's the PL uniformity that you can achieve on the 8-inch?
Well, I would have to direct you again to IQE.
Is that a question for me?
No, for Ivan from IQE.
Okay. I do have one very brief slide which I can share with you if you wish.
I don't know. Maybe we're running out of time here. I don't know.
If we're running out of time, what we're seeing is an equivalent uniformity, PL uniformity of the active region, an equivalent reflectivity uniformity, but improved surface morphology on germanium. That would include 150 millimeter germanium against its equivalent gallium arsenide, where I think the substrate, the gallium arsenide substrate maturity is long term. And as Ivan's pointed out, 8-inch gallium arsenide is still relatively new, but certainly germanium is demonstrating much better morphology, but equivalent in terms of PL uniformity, line widths, and a reflectance uniformity over the wafer. So we see no degradation in materials characterization moving to germanium. That's what I wanted to point out. Okay, Karthik?
Yeah, thanks. Yeah.
Thanks a lot, Ivan. If you want to go deeper in the discussion, you can ask us to be put in contact. Eric and Karthik, please feel free. Okay.
Yeah. Contact me. Yeah.
Thanks a lot, Ivan, for your relevant presentation.
Thank you.
And now let's welcome Christian Neumeyr from Vertilas, please, Christian.
Right. Good afternoon.
The floor is yours.
Hi. So my screen should be shared now. Can you see my screen?
Yes.
Yes.
Great. Okay. Thanks. So good afternoon. Thanks very much for showing our technology today. So this is Vertilas, Christian Neumeyr, and it's a presentation about our indium phosphide long wavelengths VCSELs. So we provide single mode and multi-mode VCSELs for optical communications and sensing. And here's a quick agenda. We have a quick look at the structure of our technology and design, quick look at the markets, then some information on the tunable VCSELs for the gas sensing market for TDLS systems, high data rate VCSELs for optical communications, and then finally new products, 2D VCSEL arrays for 3D sensing in a quick outlook. So Vertilas, that's now 20 years of VCSEL innovation. So we have been founded back in 2001 And over the 20 years now, we have developed our technology and a wide product portfolio and developed many customers all over the world to become a leading supplier of long wavelength VCSELs. So to the left, you can see a quick look at the structure of our technology. We have basically an epitaxial DBR, an active region. The current confinement in our technology is done with a buried tunnel junction, followed by an indium phosphide regrowth layer. And
we cannot see your slide.
You cannot see my slide?
No, I can.
I can.
Yes, on my side, that's okay as well.
You can. Everybody can see? Okay.
Yeah, you can continue.
Yes.
Okay.
All right. Thank you. Okay. And as was mentioned in the previous presentation, that if you go from gallium arsenide to indium phosphide and you want to get a high reflectivity mirror, especially for the back mirror, you need many mirror pairs. So we have solved this by replacing the epitaxial DBR with a dielectric DBR, which gives a number of benefits in our design. And at the bottom, we have basically a galvanic pseudo substrate, which acts as a very nice heat sink. So in summary, we have an optimized thermal design. The current confinement is done by a buried tunnel junction. Our lasers are polarization stabilized, which is critical for many markets and applications. We have been running a 25,000-hour accelerated aging campaign. On top of that, a 50,000-hour age-toll campaign. And the device is passed against the Telcordia requirements. We provide singlets, 1D and 2-dimensional arrays, and we can address applications starting from 1.3 micron all the way up to 2.3 micron with our single mode and multi-mode lasers. So far, we have been focusing mostly on optical communications as well as the TDLS market. But on top of that, now we are developing a new product portfolio with 2D VCSEL arrays for the 3D sensing market. Now let's have a quick look at the tunable VCSELs for the gas sensing TDLS. To the left, you can see our standard product range starting at around 1.3 micron for hydrogen fluoride detection, and that's going all the way up to beyond 2 micron. And there are many TDLS gases in between, moisture measurements at 3092 or 8054, ammonia, carbon monoxide. Methane has already been mentioned in the first presentation, hydrogen chloride. So there are many standard products we manufacture, but on demand, we can manufacture actually any wavelengths in this range. We have different types of packages, cooled and uncooled, open packages, or like with a cap with integrated windows, or fiber pigtail packages. What's very important, of course, the tuning for this TDLS market. Our lasers can be tuned by around 4 nanometer by bias current. And the lasers, what's also extremely important is, of course, its single mode performance. It's got a like 40 dB or more at side mode suppression ratio, as well as a very, very good narrow line width of these lasers. Okay, looking at the next market, optical communications. We can produce products here for all kinds of bands, O-band, C-band, L-band. Our lasers can also be integrated with silicon photonics and show very high performance. So the next slide shows you, for example, a 1310 nanometer laser for 10 gigabit applications. What's really important is really that those are uncooled applications, that the lasers not only perform at low temperatures, but also at very high temperatures like 80 or 90 degrees. Here's an eye diagram where you can see a 75-degree eye with a mask margin of 40% and extinction ratio close to 5 dB. We have an even faster product version, which goes up to in NRC with no equalization. It's a 25 gig laser, which provides a mask margin here of 26%. We have a similar performing laser also for 1310. And for these products, also this equalizer, 50 gigabit NRC modulation has been demonstrated. Of course, you can go to even higher data rates if you apply DMT or PAM4 modulation. Here's an example of a silicon photonic integration with our VCSELs. This is from the EU project Passion. And I saw that Giovanni Del Rosso from VTT is also in the audience. So if you have any special questions to this, we can ask him later. But this is a highly integrated 2 terabit transmitter chip. It's a PIC with 40 VCSELs are flip chip bonded. So you can see here a sketch. So this is 1 VCSEL on each side. You have 10 VCSELs flip chip bonded. Here you have a zoom in. You can see the 3 contact pads for this VCSEL chip, and then those lasers are flip chip bonded face down and are coupled into the waveguides with a 45-degree mirror. And by that, you can integrate a very small form factor, 40 VCSEL chips, and they were driven by DMT up to 50 gigabits. So you had a 2 terabit transmitter and a very small form factor. And of course, here the VCSEL part is very important, the performance and the low power consumption. Okay, so let's move to the next or the last product range for today. 2D arrays for 3D sensing. There are many applications, just to name a few: robotics, face recognition, in-cabin monitoring, autonomous driving, etc. So more and more questions or inquiries come up where people are looking into long wavelength VCSELs like 1.3 micron and beyond, especially in the range or because of eye safety, has also been mentioned before. Reduced sunlight interference, so around 13-15 nanometer, for example. This is better than in lower wavelengths. In any kind of special application or general markets that require from their system higher wavelengths. We have produced a number of 2D arrays. So they started, it could be a single emitter, could be 3 emitters, but smaller ones like 12, 24, or all the way up to 800 emitters, and they can even be increased to 1,000 or more. So we can have any number of emitters almost, starting from a few milliwatts to tens of watts in pulse mode. The emitters can be single mode or multi-mode, and the configuration can be designed per demand. Here's an example of the 800 emitter array. So in QCW mode with a 300 microsecond modulation, you can bring it up to 8 watts or more. If you increase beyond 30 watts, you probably might get close to 9 or 10 watts even. Here's another example. It's a 300 emitter array, which produces a little bit over 3 watts in optical power in QCW mode. And if you drive it in pulsed mode, it can even go up to 14 watts. So almost a factor of 5 more than in QCW. Okay, so that brings me to my summary. So this technology, indium phosphide VCSELs, allow to address 10 to the 100 gigabit optical communications. Of course, in a module level, that's a multiple of that. Integration with silicon photonics. You can manufacture high-power 2D VCSEL arrays. This technology, if you go to gallium antimonide, you can go even beyond 2.3 micron. And we also have a prototype technology for wide tunable VCSEL, which gives you about 50 to 100 nanometer tuning range. Brings me to my end. Thank you very much.
Wonderful, Christian. Thank you so much. Really appreciate this. And also really liked all of your different presentations. And I wasn't aware that you had done the Passion project. So that was fascinating. So are there any questions for Christian? Okay, we have one from, I'm sorry, I'm probably going to mispronounce your name. Frederic Zanella, do you have a question, please? I'm sorry, Frederic, you're muted.
I'm sorry, thank you. Yes, it was me indeed having a quick question. In all those slides, or especially the slide, I think it was 10 and 11, where we see a top view of the chip, we really see the circular area where you have the VCSEL. It's quite dark. Is it really the the bare surface where the emission occurring, or it's an optical system on top, like a micro lens, for example, to beam shape the emitted beam.
You said slide 11, right? Let me maybe.
I think we added in every slide in the bottom right. We see also a quick.
This one. Sorry, this one here. Or I'm not sure.
You are not sharing yet.
I'm sorry. You're. I could hardly understand the audio was not very good. You said slide 11.
Yes, please.
Let me just jump back to slide 11.
Is the audio better?
Yeah, this is better now. Yeah. Not sure which slide, or this one.
We could see a chip overview.
Yeah. We can't see your screen, Christian.
If you can share it again, please, Christian.
Ah, is my screen not shared anymore? That's kind of strange. Okay. I need to go back to presentation mode. 1 second. I move around. Give me a sec. I move around my PowerPoint so that it works faster. Okay, should be back now.
Yes.
Yes.
Okay, sorry for that.
So in all the zoom-in pictures, we really see the disk, the circular area, which is quite dark. So is it directly the bare surface, or there is, for example, a lens on top also to further collimate the beam?
You mean for this? Sorry, the audio. I hope I'm not. My hearing is not getting so bad.
No, I had a difficult time hearing it as well. Although we're probably about the same age.
What I understood is that, are you asking that for this type of integration with silicon photonics, coupling the light into the waveguide, if you need like a lens or anything? Is that your question, or?
Yes, for example, yes. If you have on top, if it's something that would be interesting to have also a lens.
I hope I'm answering the question correctly. We don't have any lenses today right on top of the laser. Of course, we are investigating always and we have tested this actually to have like micro lenses directly attached to our VCSELs, even on wafer level. That has been tested. I haven't shown any application in this presentation or any product, because this passion project, we didn't need this type. It was a lens, not a lens application. It was a 45-degree mirror coupling into the waveguide. But yeah, of course, it would be very interesting if you combine micro lenses on wafer level with the VCSELs on wafer level. Yeah.
Thank you for the answer.
And please send me an email also if I didn't catch all the details of your question.
Okay, wonderful. Thank you, Christian, and thank you too, Frederick. Let's see, there's another question from Karthik. Two questions, actually. Karthik, do you want to ask your question directly, please?
Yeah, sure. Thanks, Christian. It was a really informative presentation. I'm always looking for challenges for our devices. One question was, you mentioned the long wave 2D array VCSELs and a bunch of applications that you had mentioned. You mentioned LiDAR as well as one of them. Are the VCSELs matrix addressable, or are they kind of just like they go on and off together completely?
The ones I showed today, they all emitters switch on and off at the same time. But of course, you can structure the device into sections or rows, for example. We do not have a matrix addressable solution today where you can actually individually switch on each emitter. That's not available today.
Mm-hmm. Okay. And my second question was, the principle for the high power 2D arrays that you mentioned, like with 800 emitters and so on, are they using multi-junction, or how are they getting this high?
The products shown today are single junction lasers. Of course, we are looking into ways to further increase the optical power from one emitter. So from the examples today, those are multi-mode emitters that I showed. And each single emitter produces at rollover say around 8 to 10 milliwatt of optical power, depending on the active area. Our single mode lasers are more like about half of it at room temperature, say 4 milliwatt or plus. Although for our like communications applications, it's not so much the optical power at room temperature, it's more that they perform very well also at like 80 or 90 degrees, nice threshold in a good optical power.
Ah, okay.
But those are all single junction lasers.
Single junction. Thanks a lot.
Very good. Any other questions? Wonderful. Okay, Christian, thank you so much. We're going to go to our next speaker, who is Roland Roos. And again, please I apologize if I mispronounced your name. And Roland is filling in for Julien Boucart. So Roland?
Absolutely. Hold on, let me share my screen.
Thank you. Yes, please.
All right, I think I'm sharing my screen now.
Let me swap mine here.
Yeah, all good, Ronnie.
Okay, sounds good. So today, I'm just going to cover a few of the emerging applications for VCSELs in the different areas. For in-cabin automotive, different applications for OMS, DMS. Also, then we've got AR, VR is becoming certainly more popular for VCSEL technologies. So integrated more, moving away from LEDs and more toward VCSELs. And then you've also got long-range LiDAR, external LiDAR, moving from edge emitters to VCSELs as well. And then you've also got robotics, autonomous vehicles, robotics for either outdoor delivery type applications or for indoor warehouse applications. We're seeing in the in-cabin automotive, for even in the in-dash or in the rearview mirror, we're seeing applications where there's a wider FOI, at least 120 degrees and above. There are applications too where they're putting the cameras in the roof of the car. And then to capture the corners of the car for the whole cabin, you'd have to get above, say, 150 degrees. So there are applications for kind of ultra wide FOIs. LEDs have difficulty at these larger FOIs, so it may be that VCSELs may start to gain ground here from an in-cabin perspective. From a LiDAR perspective, I think what we're seeing there is addressability, right? Multiple channels, if not 20 plus channels. So there's a issue there on power per emitter, right? Maximizing the power per emitter at these very short pulse widths, very low duty cycles. Also, obviously, the extended temperature range. I don't think that's new. And then the other, and all of this too, even beyond the VCSEL technology is, if we do have 20 channels, how are we going to address those? What sort of drivers are we going to build? Beyond the individual emitters, there may also be a reason on the driver's side to have a common anode VCSEL as opposed to a common cathode VCSEL. You could decrease the number of capacitors in those multi-channel drivers. From an robotics standpoint, certainly from an outdoor perspective, certainly folks have talked about the longer wavelengths. What we're seeing is even at 1380, there's a significant advantage over the 940, especially in direct sunlight. These 940 TOF cameras are fairly blind with a high reflective surface or with direct sunlight. So if you want 100% coverage in your outdoor applications, you're going to need to go to the longer wavelengths. In that vein of the longer wavelengths, one of the things that we're looking at are to expand the current platform, right? The current gallium arsenide platform that can get to things like 1100 nanometers to try to increase functionality for the current platforms, VCSEL platforms. And then also on the further wavelengths, the 1380s and above, looking to create new platforms for VCSEL technology in particular. But the other thing that we are doing at 2.6 as well is we've got, the edge emitter indium phosphide that we leveraged on the datacom side. We're leveraging that here to create just initial samples for customers. High power, 3 watts, 2 to 3 watt power modules that they can put in their cameras so that they can start to create these prototypes for customers. We've seen, some really good initial test results from a few different customers on this, where you can obviously see do a different level of discrimination at 1380 with different sensors. You can see water levels differently. You can see people discrimination with hair is white at 1380. So different things where you think that there's probably a fourth dimension of discrimination for some of these sensor applications. And then the other is, like I said, these outdoor long range sort of 10 meters and plus applications where we're seeing that that these illumination sources work much better with the direct sunlight. I think the other added functionality at the chip level, obviously, I think someone was talking about multi-junction. Certainly multi-junction is something that's starting to become more popular here in the last couple of years. Reliability on these chips is not an issue any longer. We could reduce the EMI, obviously, with less current. We can lower the chip size to lower the cost of these. So I think that's important. I think the other thing too with the multi-junction, with the 5-junction and the, up to 8 junctions in some cases, if you run at these really short pulse widths, 5 nanosecond pulse widths, at very low duty cycle, though, at something like 0.1% duty cycles, you can really push these devices to very high peak currents or peak powers for some of these longer range LiDAR applications. Again, you also, in some cases, they want to do multi-channel, so you're going to need these high powers, on individual emitters. So there may be a push. There's also a push to get these emitter sizes up, 20, 30, 40, 50 microns instead of the, kind of standard 10 microns for some of these high-powered arrays. I think the other thing that we're seeing more on the mobile side is the polarization, certainly on AR/VR, also on just general TOF cameras. How can we leverage the polarization of VCSELs? Even without gratings, but if we put gratings on it, it gets even better. Is there a way to do sort of hybrid solutions with these sorts of VCSELs? Is there a way to reduce crosstalk on some of these cameras? So, these sorts of things are what folks are looking at with some of the polarized VCSELs, and the attenuations. We're not losing any more than, say, 10% of power at the given polarization. So you're not losing a tremendous amount here by going to polarization on the chip. So, so some advantages there. The other thing that we're seeing, we've been doing a lot of package technologies and designs over the last couple of years. So what we're seeing from a flood illuminator perspective, from a package standpoint, is eye safety is obviously concerns of things like ITO traces, things like MPDs, monitor photodiodes within these systems to monitor that. The other thing that we're seeing beyond just flood illumination is dot projectors, right? How can we take this light and put it into dots and then project that light even further to increase distance and range on some of these cameras with lower power levels, also to increase eye safety. So we're seeing all of that. On the integrated driver side, another piece where eye safety is important. How can we build a full 3-in-1 module with the driver that will have all of the cutouts and the safety switches for too much power, or if the optic falls off, ITO, things like that. How can we build that into a full module for customers so that we can then classify this as class 1, and taking that off the backs of the tier 1s or the integrators. And then the other one, as I talked about previously, for kind of OMS and occupancy monitoring within the cabin, are some of these ultra wide fields of illumination, where we're talking about 150, 160 plus, and then again filling the corners of the cabin. And to do this, right, you're probably going to need more than one optic to get this, right? Standard diffuser technology is not going to get you there. But then once we start to build these multiple optics parts, making sure the materials and the processes that we have for putting these parts together can be automotive compliant and survive these kind of harsh, high temperature environments. So I think I'll end it there and open it up for questions.
Wonderful. Thank you so much, Roland. This was
Sure.
very good. And it was interesting to see the new applications that you're looking for as well. Here, let me get back to the grid. There we go. Are there any questions for Roland?
Yeah, I have a question, Karthik here.
Sure.
Yeah, I just saw the ultra-wide VCSEL for OMS application going beyond plus minus 80, 85. How are you doing the beam shaping, beam profiling? Are you using goniometric solutions, or how are you managing that with such high divergent beams?
Yeah, how are we measuring it, you're saying?
Yeah, exactly.
Yeah. You're right. You absolutely got to use a goniometer, just standard goniometer techniques to measure those. And then, yeah, I mean, irradiance is not really.
Okay. Yeah.
Yeah, not really a factor here. But yes, absolutely, standard goniometers at this point.
All right. Thanks.
Yep. Sure.
Great. Thank you, Karthik. And then ST Microelectronics, Eric.
Yes. Thanks for your presentation, Roland. Very
Sure.
interesting. Can you comment on the motivation / interest for controlled polarization? I did not catch what's the interest.
Yeah, our understanding of most of this, at least from a mobile perspective in a phone, is crosstalk, right? There's this crosstalk between the illumination source and the sensor on the cover glass. And if you can polarize the light, you can minimize this crosstalk. I mean, I think there are folks who are already using, someone talked about the natural polarization of VCSELs in general without even putting gratings on it. There is a certain polarization bent, and there are already folks who are kind of leveraging that in this crosstalk. But if you can actually put gratings and guarantee the polarization, then you can have that sort of functionality. The other piece is folks like Metalens have talked about a hybrid. I talked a little bit about a hybrid solution. So you could do a flood or a dot projector potentially with one die. You could have every other row be a different, 0 or 90 polarization, and you could have an optic where that optic is aligned in such a way that, for one polarization, you get a flood illumination, and for a 90-degree polarization, you get a dot projector.
Okay.
And this way you can, on the chip side, there's probably not a huge cost advantage there, but on an optics side, there probably is, right? You could have a single optic. You wouldn't have to double up your optics for this hybrid solution. So those are probably the two main things that we're seeing. And there's a bunch in the AR/VR. I'm not as familiar with the AR/VR market, but I know that in a lot of the AR/VR applications, polar locked is also important.
Okay, great. Thank you so much.
Sure.
Oh, sorry. Thank you, Eric, too. And Christian, you have a question.
Actually, also wanted to comment a little bit on the last question about the polarization control. That's also very important for our products and working with our customers. And if you look at the parameters or the measurement data of the VCSELs, if you see a polarization flip, you can see a change in optical power as well as a slight change in wavelength. And that is critical, like for any kind of sensing or datacom application, that you don't have that. So this actually controlled polarization that also we have implemented. It's not natural polarization in our lasers. We have actually a design method for that and a manufacturing method. But I would think that this also would impact for 3D sensing if you have these flips that would actually distort your signal, especially your detector would get irritated by that if you have slight changes in optical power or wavelength.
Okay.
Good comment. Okay, Eric, do you have any additional questions? I see you still have your hand up.
No, that's just I forgot to lower down.
Oh, no, it's okay. It's okay. Okay, and Kristen, do you have another comment or question?
It's just impressive, the technology and the maximum power that can be achieved, especially with this ultra short pulses. Unfortunately, we don't have those ultra short pulse set up here. I would like to bring my lasers maybe to to SIX to you, and if Roland, if you could test our lasers, see how much we can get out. So the data I showed with the 300 emitter array with the 14 watts, that was a 200 nanosecond pulse. So I think, and you can still see a rollover. So it's still a relatively long pulse. So of course, having like a 5 picosecond pulse or something.
No, understood. Yeah, no, and in reality, what we do is just do existing die attach to existing boards, right? I mean, we have no way to measure this beyond that. So
yeah, okay.
Just using the existing EPC or whatever boards that we've got to die attach these. There's really no other way that we've got at this point. We are working on talking about testing, working on platforms where we can do the reliability of these devices at these very short pulse widths as well, right? So, what are the mechanisms potentially for reliability that may be impacted by these high current, low duty cycle type applications? So that's the other piece that we're doing a lot of work on as well.
Cool. Thanks.
Yep.
Okay, wonderful. Well, let's see if there's no more questions for Roland at this point. By the way, at the end of the sessions, we will have an informal session where you can stay and ask additional questions if you'd like. But right now, let's move to Nikolay. I'm going to screw this up again. Ledentsov with SIT Systems.
Hello.
Hello.
Can you hear me? Yeah, great. So the company is called BI Systems.
Excuse me.
No problem. For vertically integrated systems. And I will speak today about VCSELs and more specifically multi-aperture VCSELs, which we think would be will have an application in Wi-Fi, optical wireless, and 100G applications. So let me quickly introduce our company for those who don't know. So we were established in 2006, and we are developing VCSELs for now. Our main focus is datacom VCSELs for short reach interconnects emitting at 850 to 940 nanometers. We also have other R&D products and prototypes, but this is our main focus. We do from simulation. We're fabless, but we produce our VCSELs on 4-inch wafers with more than 100,000 chips on one wafer with 250 micrometer pitch mostly. We have VCSEL products, PDs, which were qualified last year from 850 to 1.5 indium phosphide, and also custom multi-aperture VCSELs. We do packaging, high frequency packaging. Here, for example, you see a 70 gigabit RSI of such an assembly with our IC and VCSEL. Here is a short update of our most recent results. It's 100 gigabit per second PAM4 with VCSELs, so with very low TDCQ, 106 gigabit per second with InFi driver. Here you see a paper published by Huawei. They used our this VCSEL fiber coupled VCSEL module. They achieved 200 gigabit per second PAM4. This is on OFC 2022, we presented 100 gigabit on 4 parallel channels with shortwave individual multiplexing. So the total capacity of such a link would be 400 gigabit per second and even more with other modulation formats than PAM4. And also with Heinrich-Hertz Institute, we have previously demonstrated 224 gigabit per second on single channel with 850 and 910 millimeter VCSELs. So the VCSELs that we develop are very fast, and I will tell you why we're moving forward with multi-aperture VCSELs that I want to introduce and make a focus of this presentation. So here you see a 3D render of such a chips. We call it a compact mini array. Multi-aperture, you see 4 emitters very close to each other. And the reason why we focus on this is that this chip version breaks the dependency between the output power, the spectral width, and the high-speed performance of the device that I will explain just in a moment, not going too much into the technical details. So what is the motivation behind those VCSELs? There are 2 main aspects here. One is the wish to have high-power single-mode VCSELs and use VCSELs for optical wireless. So for single-mode VCSELs, the motivation behind this is that in hyperscale data centers, we have distances of transmission with fiber up to 2 kilometers. And of course, if we use multimode fiber and multimode VCSELs, the transmission distance is limited to 100, 200 meters. And using single-mode VCSELs and multimode fiber, one can extend it to 2 kilometers, allowing this low-cost technology to cover the whole distance in data center. Transmission distance data centers. If we're speaking about next generation VCSELs, which will be modulated at 100 gig PAM4, then to transmit above 100 meters, we need very low spectral width to reduce the chromatic dispersion. So even with the next generation, regular VCSELs with 0.4, 0.5, even 0.6 nanometer spectral width are too broad to transmit to 100 or 200 meters. This is why the demand for low spectral width is even higher now with these speeds. And for sensors, for low-cost fiber sensors, having single-mode VCSELs is fast single-mode VCSELs is also a benefit. Now we speak about optical wireless. What are the requirements there? So now the motivation behind Li-Fi is that, for example, in military applications, one doesn't want to have a detectability of a radio signal. So having a light distributed Wi-Fi, for example, one would be able to only have signal inside a room. It will be blocked by walls, and this won't be detected outside of this facility. For 5, 6, or 6G, we would have access points, very close proximity between each other, and maybe in some places where it's not easy to bring all the cabling between them. So having wireless transmission there might be also a benefit. And in enterprise, of course, to avoid radio signal overcrowding of the space with radio signal, maybe Li-Fi has an opening. This is a very new field. We think that VCSELs have an opening right now. Many Li-Fi systems employ LEDs, which are of course not so fast, but yeah, they are currently used. And here I want to show you how these multi-aperture arrays solve the problems of these 2 applications. In single mode VCSEL transmission through multimode fiber, we need a reduction of chromatic dispersion to increase the transmission distance. And what we want to target with this design is reduction of spectral width while maintaining the same output power and high bandwidth. And for optical wireless, what we want to achieve is to increase the output power while maintaining high bandwidth and directionality of the light, and achieve at minimum more than 50 milliwatt output power at, let's say, 20 gigahertz bandwidth. And in the future, multi-aperture arrays have the potential to increase the bandwidth of the VCSELs by photon-photon resonance. It's an effect also already demonstrated in edge emitters, and also reported for VCSEL, for example, from Ken Chakat group in Blanche-Champagne University. So the concept of mini arrays has been reported previously, and also coherent arrays for sensing a long time ago. And our group worked on that a long time. The idea is that one puts two different VCSELs very close to each other, maybe below 15 micrometer distance. And to realize that, one needs to oxidize through holes. And here you see two pictures of two VCSELs. One is a compact mini array, and regular VCSELs. You see they have the same footprint. And of course, the emitters here in the center are located further away than the small active region in the center of the regular VCSELs. As I will show in a minute, efficient fiber coupling can be achieved, and also yes, the active area in these two VCSELs is approximately the same. So when we compare these two VCSELs, we see that the thermal rollover in mini array is further away. The output power is very similar. The threshold is a little bit higher because we have 4 emitters, not 1. But the 80% fiber coupling to OM3 fiber can be easily realized. But the main benefit, and in this sense, these chips are very similar, but in their spectral width, they are very different. You see that the multi-aperture array has nearly a single mode spectra, approximately 0.1 in RMS. And here you see the far field. So of course, the multi-mode VCSELs shows a donut-shaped far field as usual, which is not very desirable fiber coupling, but the single mode multi-aperture chip at the same output power shows very beautiful Gaussian profile with full width up max of around 10-12 degrees. And this is what enables it to have efficient fiber coupling. Here's some high-speed results. We have C550 gig I. This is not the most recent. I will show a little bit later most recent results with better, better high-speed performance. What is also important and interesting is that we see coherent emission on these chips, and these are important for this photon-photon resonance in the future development, or also to creating beam steering in sensing applications. This is, of course, very a topic for R&D. This is not yet demonstrated, but we see different output modes on these VCSELs. And this is the last one is my favorite. It's holes, a state of holes in the far field profile. So now I want to show you, so as epic motto is what we can do for others, and what we seek is we have now available prototypes of these chips that we can distribute amongst partners if interested. One is a 100 gig PAM4 curve here with 4 milliwatt output power at the maximum. This is, I think, with open detector, not fiber coupled. As you see at 850, the spectra is very narrow. So this is a purely single mode emission. At 7 milliamps, the eye diagram at 50 gig and eye is clearly open, error-free, without any additional equalization, meaning that we cannot test it right now, but we assume that 100 gig eye will also be error-free with a little equalization. And the bandwidth is around 25 gigahertz and reaching up to 30, which very high bandwidth. So these are the versions with which we want to work on single mode through multiple fiber transmission in datacom. And for Li-Fi, we have packaged such modules. We have a high frequency V connector on which we wire bond directly the VCSEL itself for quick measurements and testing. It requires external bias team and current supply to use, but it's very, very simple to use. Here you see a 25 gigabit eye diagram without equalization, so it's also very well open. But the most important feature of this particular chip is that it goes up to 50 milliwatt output power at this speed. So maybe in our opinion, the output power bandwidth product of this device is very, very high. And we are seeking people who will be interested to test that in Li-Fi scenarios to see if these VCSELs indeed would satisfy the requirements. Especially, and these VCSELs emit at 940 nanometers. Because of this is of course better than 850 for eye safety concerns. This is this is what I wanted to present to you. Here's some other updates about what can be reached with our VCSEL technology. And if you have any questions, I'll be happy to answer them. Thank you.
Wonderful. Thank you so much, Nikolay. This was really interesting, and I like the VCSEL arrays, and I continue to be surprised by VCSEL technology, not just doing simple interconnects within the data center, but extending the reach, now doing Li-Fi and doing additional applications as we've seen through these presentations. Are there any questions for Nikolay? I see one. Rayan Ghani with ficonTEC. Please excuse me. You are
Hello?
muted. There we go.
Yeah, can you hear me?
Yes, thank you.
Yeah. Hello, everyone. This is Rehana from ficonTEC. I'm R&D engineer at ficonTEC. Actually, I have a question about your VCSEL characterization that you did. Do you have an automated system for this measurement, or is just a manual measurement setup?
Yes, so we have a mapping machine that we use for the characterization of all our VCSELs once they are produced. And in-house for the more complex things like far field, near field, this is of course custom setups. And this is why we automated them ourselves. Yeah.
Yeah, because you mentioned at the end you are interested for the characterization of your new products. Actually, we have a wafer level testing system as one of the fields that we are working now is VCSEL testing. We have automated system that can use for VCSEL characterization, but in R&D we are really interested to have a collaboration to develop our system. Of course, we have some results for our previous customers, but later I will send you an email. Maybe we can start a collaboration that tests your VCSELs and in parallel we develop our systems.
Yeah, that would be interesting. So we have a mapping machine that can do LIV and spectral measurements. But for example, in the future stages, what would be really exciting is to have a mapping machine that would, for example, test high frequency parameters on the whole wafer. But we were not brave enough to go on this endeavor. Maybe this is something that we can do. That would be interesting.
Yeah, for sure.
Yeah.
Okay, thanks.
Wonderful. Thank you. Thank you very much, Rihanna. Let's see. And Christian had another question too, please. And you're muted.
Hi. Okay. Yeah, great. Wow, very impressive data, I have to say.
Thank you.
Absolutely. So your idea with the four emitters, and you say they behave like one single emitter in the end, or because you said you can couple them into a single mode fiber, like a standard single mode fiber. And how do you do the coupling? It's like still you use ordinary lens or?
Yeah. So we couple them to multi-mode fiber.
Multi-mode fiber.
Yeah. So this is easier, but
okay.
I think
single mode emitters, but then you couple them in. Okay, I misunderstood that. So it's into multi-mode fiber. Okay.
Yeah, but the far field profile of them is you see is nearly Gaussian. So this is why coupling to single mode fiber is also possible. I think we tried it once, and we. For example, for multi-mode fiber, we got 80% efficiency. And for single mode, I think we got also very high, like 60, 65. It's a lot of power inside the fiber. We use a lensed fiber for that.
Mm-hmm. Lensed fiber, okay. And then on your performance, also astonishing really what you get out of your VCSELs, 25 to 30 gigahertz, you know, PAM4, 106 gigabit is pretty amazing. What was the biggest challenge for you to get to this bandwidth? I mean, usually it's either photon lifetime or it's the intrinsic parasitics, right? So can you share just a little bit how you got?
Yes, this is a combination. So I personally am more in the characterization in the company. So my colleagues would probably be able to elaborate much more details about.
No, it's okay.
Yeah, but this is a combination, of course, of all the factors, and this is a long road that you see. As you know, all the VCSEL manufacturers are going this road, this long road into perfecting the VCSEL day by day.
Yeah.
This is.
Do you have one data point? Maybe that is something you measure. Is what's the performance, the bandwidth at, say, at elevated temperature, say maybe at 70 or 80 degrees compared to room temperature?
It's very similar. So, for example, on our website for this multi-aperture, I have already put out new data sheets, and there we have S21 parameters at 25 and 85 degrees. And for the particular chip that I showed, we just had a 2 gigahertz, 3 gigahertz lower bandwidth at 85.
Even more amazing. Great. Congratulations.
That's not always the case, but for this one, it was very temperature stable.
No, great. Congratulations.
Thank you.
Okay, so we're running a little bit over on time, but we have one more speaker. So would like to pass the baton to Ludovic Marigo, and please excuse me if I mispronounced your name, with NILT.
Oh, good. Let me just put the right. Here we go. Yeah, so good afternoon, everyone. So I'm Ludovic Marigo, product designer in NILT, and I will discuss today about diffractive optical elements and their integration on the VCSEL for tough applications. So first, allow me to introduce our company. I'm not sure that everybody knows us. So we have a headquarters in Denmark, in Copenhagen, where we have our optical design team. And then we have 3 sites for the mastering that we are doing by e-beam lithography. So we are doing that in Denmark, in Sweden, and also on the East Coast. And then we have R&D also in Sweden and Denmark, and we have all the engineering, prototyping, and then the process and product development in close to Zurich in Switzerland. So our key technology is really the diffractive optical elements and the MOEs. We are also doing gratings and MLAs. And the historical background of the company is really the mastering. So we are also doing a lot of masters for AR and MR display to make the diffractive planar waveguides. In terms of element that we are doing, so we are either doing we are either doing single elements, so on only one side of the glass, and we are doing that by nano-imprint lithography, I guess you would have imagined. And then we can also do some components. So we can have different optics, so a collimator, and on the other side we can imagine to have a diffuser or a fan out, and we can stack different wafers together. And we are also working on module, and then for AR displays. Our main, I'm sorry, trying to go to the next one. Okay, so here are the different elements that we are doing. So as I said, we are doing diffractive optical elements, such as diffuser. We have different press release, so with very high efficiency and extremely low zero order. Currently we have some FOIs higher than 70 degree. And yeah, as Ronnie mentioned, we are also going in the direction of the very wide FOI, so higher than 100 degree. We are also doing some fan out, and I will discuss about that today. So about the dot projector, collimator, focusing lenses. And then another aspect of the company is about the meta optics element. Here again, working for smartphone, automotive, industrial, medical application, but also for polarization control, which as mentioned in the previous talk, is also a hot topic here. And we are also doing the master so for the display, so where we are directly doing the e-beam lithography and we are directly selling the masters to our customer. And so today I will discuss mainly about the diffractive optical elements and about the fan-out, so for a dot projector. So what we are doing with these diffractive optical elements is that, as I mentioned, we can do either single-sided elements. Another thing that we can do, and to have a very compact solution, is to have a collimator on one side and the fan-out or a diffuser on the other side of the glass. So really to have a very compact solution here. And we have, of course, very deep understanding of the alignment requirement, and because we are a fully integrated company, so we can really help our customers to build the module and to understand what is the tolerance needed, or what will be the impact of misalignment. Another interesting thing that we can do, thanks to nano imprint lithography, is that we can have two different DOEs on one side of the glass. So you can imagine if you want to have either a very large VCSEL arrays or an addressable VCSEL array, you can have one part that would go to a diffuser, another one that would go to a dot projector. Of course, everything would be integrated with ITO or with a photodiode also for the module level. So you are really gaining a lot of space. Instead of having several VCSELs, several substrate drivers, you would have only one element. And yeah, of course, the overall system and the assembly complexity can be reduced. And also because we are not working with refractive optics, but with these DOEs, we can also have a better alignment, easier alignments for the pick and place also, because our DOEs are flat optics and they are more or less the same dimension or the same aspect ratio than the VCSEL. So you can have only one DOE on top of your VCSEL, and then on the receiver you can have a meta optics, for example, with a sensor. So you can see that we are reducing the complexity of the module in terms of alignment, and also for the pick and place. And as a side note, because I know that most of the module currently are VCSEL with a diffuser on top. But of course, if we discuss about a collimator and the fan-out, you would need to consider that the collimator needs a specific alignment in terms of the Z direction, and the fan-out in terms of the theta, so the angular alignment. So that would need to be considered in terms of design space for the module, and also how do we assemble the module with our partners. So about the spot illumination, I want to mention first thing about illuminating a scene with a uniform dot pattern, and how does that work? So the fan-out is the DOE, which is then splitting each emitter beam, which is coming into the glass, into whatever number that we can imagine. So for example, we can have a 3x3. So one beam from the VCSEL will be split into 9, or you can have a 5x3 or other dot configuration. So if you have your VCSEL array here, for example, with 500 emitters, and you want to project that at between half a meter to 10 meters, so either for the phone application or AR or VR, and then the fan-out is finally multiplying your number of dots. So the VCSEL array that you would have projected here is then multiplied like 9 times here. The blue rectangle are really here for the eyes, and that would be in an ideal world where here is demonstrated a 3x3 fan-out, which has a FOI of 70 degree by 50 degree. And of course, we are not in an ideal world, so we have some distortion at the corner here when we are getting really on the side of the optics. And when we have the VCSEL array, which has where the emitter are further away from the center of the optics. And so the fan-outs are now used, and we see more and more traction with that. Julien mentioned that too about the module. So for the DTOF, for example, for nanosecond regime, so where we want to have a very high power density, so we can use that with single junction and multi-junction. But the problem is that for that, you need a specific driver, and also for the characterization, that's also pretty tricky. So that's why we are seeing more and more traction now, thanks to the multi-junction, also for millisecond region. If you imagine to have a 3 or 5 junction, so you will increase your slope by 3 or 5, and then you can reach finally longer range with the exact same pattern and module that we had in the past. So you would have a less complicated driver and module, and that would be also suitable for the applications such as the AR or VR. What Neil demonstrated is currently some FOI, so higher than 70 degrees, so as shown on this picture here. And we are working on improving that to 100 degrees. The total efficiency, so which is really the light which is going through this FOI, has been demonstrated to be higher than 94%. The uniformity error, which is also a critical parameter if you want to have a very uniform pattern projected, so which is the intensity difference between the different tiles, so the 9 different tiles here, and we are demonstrating this number being below 10%. So meaning that you won't see any dark or very bright area on your scene that you're protecting. The contrast ratio, which is the intensity of the dot compared to the background, so how bright will be your dot, is higher than 35 dB. And of course, the spot intensity in the tile, so around this 9 time, can be tuned according to whatever customer needs. So it's really an optical design feature. And when the customer comes to us with a specific need, then we can directly design the right optic and then replicate that. But also where the fan out is also very interesting is when you want to illuminate only one part of your scene. So we know, for example, that for LiDAR application, currently we have rotating mirror or MEMS, which is very expensive and complicated, but that's the main solution. And there is more traction now about the addressable VCSEL arrays. So the idea here, and for a VCSEL array, you want to fire one row at the time for your emitters. And the goal is that since your sensor is not as precise or as good resolution as you have for the ITOF, then you cannot fire your entire scene. Also in terms of heat of your VCSEL. So if you combine that with a fan out, you can imagine, for example, to fire only one row of your VCSEL array, and then your fan out will react like that. So you will illuminate these 3 areas here, and each area will be spaced by 23 degrees in this precise case. And then you can individually distinguish on your sensors these 3 different areas. So that will enable you to be faster once you want to scan the scene. And of course, then you can define that as you want. So if you want to have the top right corner of your VCSEL array switch at first and then the bottom right, then you can always do that. But one thing to be kept in mind, and I think that's where really when we design the entire system between the VCSEL supplier, the module integrator, or the optical company provider, that because we are not living in a perfect world and we have this kind of distortion here at the center, we need to define that and to take that into account. Because once you want to have your ear perfect vertical stripe, finally you would have some emitter which would emit some light here, and because at the corner here you have lower intensity and larger spot size, finally this dot won't be very helpful. So there is some work and I guess some collaboration to be done really when we discuss about the VCSEL array design and how are we going to integrate that with the optics. Okay, try to make it short. In conclusion, so NILT is a vertically integrated company. So for optical design, mastering, replication, and then of course, optical characterization and reliability for diffractive elements and also MOEs. The spot illumination can be designed according to customer needs to achieve really compact module solution. And I think that we obviously need a close collaboration to define the optimum set of elements between the VCSEL, the collimator, and diffuser of fan out. And feel free to reach to us if you have any question or interested into the technology. Thank you.
Wonderful, Ludovic. This was really interesting. And when I think of NILT, I normally think of meta lenses, but this was so much more. I wanted to ask you one question before I let everyone else in. So you had mentioned the spot illumination can be used with LiDAR. Can that spot illumination be dynamic to be able to focus on an area of interest or not yet?
Yeah, sure, but that will come from the VCSEL itself, right? So wonderful. Okay. Yeah, we will. So I'll try to come back to it. So here it would be really the VCSEL itself, where you would have a driver and maybe you have that P down, so your very compact and integrated solution directly on the driver, and you want to fire your first row just at the beginning. And the advantage of the fan out here is that you would illuminate finally 3 parts of your scene. And here I mentioned 3, but that can be 5, for example. But really, the optics is a passive element, so you would need to fire directly from your driver and your VCSEL.
Understood. Thank you for that clarification. Does anyone else have any questions for Ludovic? No. Okay. Well, then let's wrap this up. I wanted to thank everyone for these wonderful presentations. And what did we see today? Just as a brief summary, we saw Stefano from bandwidth 10 looking at tunable MEMS with VCSELs to be able to deliver high contrast gratings. We saw Karthik, who looked at polarization testing and correction. We saw a presentation from Ivan of Umicore, who was focused on germanium VCSELs for both eye safety, as well as a great comparison between the advantages between germanium VCSELs versus the older gallium arsenide. And then Christian Neumeyr went through Vertilas, went through gas sensing with TDLS, as well as VCSELs for PASSION for high-speed communication using VCSELs. And Roland Roos of 2 SITs, applications that included in-cabin and AR/VR and LiDAR and solar. Nikolay of SITS systems, VI systems, excuse me, Datacom VCSELs, as well as extended distance VCSELs as well for mini arrays. And finally, Ludovic with NILT Technologies, how to reduce the complexity of building your arrays by using their optics as a means of increasing the fan out. Did I get those right? Great. Okay. No corrections. Okay. Thank you so much. And by the way, I'm going to stop the recording, or I'll have Neringa stop the recording, and then we can stay for the informal discussion where you can ask questions without having them recorded. Okay. So Neringa,